Myself Swapna, JL in Chemistry from Vangara.
In last class, what we discussed, that is hydrogen bond and types of hydrogen bonds, VSEPR theory and Fosson rules. Today, we are going to discuss the very important topics are hybridization
And types of hybridization, bond parameters, dipole moment, molecular orbital theory.
Now let us discuss hybridization. In order to explain the bond angle and characteristic geometrical shape of polyatomic molecules like water, ammonia, and methane, etc. This was proposed by Pauling scientists. And this hybridization theory has neither experimental evidence nor mathematical background. It is purely an imaginary theory. So what is the hybridization? The process of intermixing of an atomic orbitals of nearly equal energies of an atom to form new set of same number of identical orbitals. These new set of same number of identical orbitals are called hybrid orbitals. The process is known as hybridization.
For example, here one 2s orbital and one 2p orbitals intermixing to forms the new set of 2sp hybrid orbitals. These are almost same energy levels. So here one s orbital and one p orbital intermixing to forms the 2sp hybrid orbitals. And here one 3s orbital and three 3p orbitals intermixing to forms the 4sp3 hybrid orbitals.
In this hybridization process, only
orbitals are involved, not the electrons. Okay, and these hybrid orbitals forms the only sigma bonds, but not pi bonds. In arranging the electrons in hybrid orbitals, Hund's rule and Pauli's exclusion principles are followed, but not above principle, because of here the hybrid orbitals are degenerate orbitals. Now, types of hybridization. In this process, S, P and D orbitals are involved. As per these, sp and sp2, sp3 and sp3d and sp3d2 hybridizations. Now, sp hybridization. In this, one s orbital and one p orbital intermixing to form two sp hybrid orbitals. This process is known as sp hybridization. Here, the shape of the s orbital is spherical and shape of the p orbital is dumbbell. These two are intermixing to form these two sp hybrid orbitals. These sp hybrid orbitals are arranged in linear manner. Example,
BeCl2. In this BeCl2, beryllium is the central atom because of it has least electronegativity values when compared to fluorine.
In this, the beryllium atomic number is 4. Its electronic configuration is 1s2, 2s2 and 2p0. That is in ground state. But in excited state, the 2s orbitals are enter into 2p orbital. Then now the 2s orbital and one 2p orbitals of the beryllium atom intermixing to form these two sp hybrid orbitals. Now these two sp hybrid orbitals has unpaired electrons. Okay, now these sp hybrid orbitals have unpaired electrons overlap with the 3pz orbital of the chlorine atoms to form two sigma bonds, so that the shape is linear shape. The bond angle is 180 degrees. Percentage of S is equal to 50 and percentage of P is equal to 50. How to calculate the S percentage and P percentage? It is easy because of here in this sp hybridization only the s orbital is 1. So we need to calculate the s percentage. The s percentage is equal to only s orbital is 1. So 1 by total orbitals are 2. So 1 by 2 into 100. Then we will get 50 percentage. Same as well p percentage also. Here the p orbital is only 1 in this sp hybridization. So percentage of p is equal to 1 by total these orbitals 2. So 1 by 2 into 100 is equal to 50 percentage. Now let us discuss the sp2 hybridization. In this, one s orbital and two p orbitals intermixing to form three sp2 hybrid orbitals. These are shapes, s orbital and these two p orbitals intermixing to form these three are sp2 hybrid orbitals. These are arranged in trigonal manner. Example, BF3. In BF3, boron is the central atom. Its atomic number is 5. Its electronic configuration is 1s2, 2s2 and 2p1. It is in ground state. But in excited state, the 2s orbital is enter into 2py orbitals. Now, one 2s orbital and two 2p orbitals are intermixing to give the 3sp2 hybrid orbitals. These three sp2 hybrid orbitals of boron arranged in trigonal manner. These sp2 hybrid orbitals have now unpaired of electrons. So these each sp2 hybrid orbital having unpaired of electrons overlap with the 2pz orbital of the fluorine to form 3 sigma bonds, so that its shape is trigonal planar and bond angle is 120 degrees. S orbital is 33.3%. How? Here calculation. S orbital is equal to, then how many orbitals, s orbitals present in the sp2? Only one s orbital. So 1 by total orbitals in sp2 hybridization into 100. Then you will get 33.33 percentage. Same as well p percentage. How many p orbitals are present in this sp2 hybridization? 2 p orbitals. So percentage of p is equal to 2 by total orbitals 3 into 100. Then we will get 66.66 percentage. sp3 hybridization. Then one s orbital and three p orbitals intermixing to forms the 4 sp3 hybrid orbitals. Here s orbital shape is spherical and 3 p orbital shapes are dumbbell. This is the px and py and pj bz. These orbitals are intermixing to form the 4 sp3 hybrid orbitals. These all are 4 sp3 hybrid orbitals. These are arranged in tetrahedral manner. Example, CH3. In CH3, the carbon is the central atom. Its atomic number is 6. Then its atomic number is 6. Its electronic configuration is 1s2, 2s2 and 2p2. It is in ground state. Then in its excited state, the 2s orbital is enter into 2p z orbital. Now one 2s orbital and three 2p orbitals of the carbon atom intermixing to forms the 4 sp3 hybrid orbitals. These are 4 sp3 hybrid orbitals. These are having on page of electrons. These 4 sp3 hybrid orbitals, each sp3 hybrid orbital is overlap with the 1s orbital of the hydrogen atom to form 4 sigma bonds. The shape of the 1s orbital is spherical. So that these all are sp3 hybrid orbitals. These are overlapping with the 1s orbital of the hydrogen atom to forms the 4 sigma bond. So that the shape is tetrahedral. The bond angle is 109 degrees 28 minutes. Then S percentage. In this sp3 hybridization, how many s orbitals present? Only one s orbital. So percentage of s is equal to 1 by total number of orbitals in this sp3 hybridization. So 1 by 4 into 100. Then we will get 25 percentage. Then percentage of p is equal to, in this sp3 hybridization, how many p orbitals are present? 3 p orbitals. So 3 by total number of orbitals. 3 by 4 into 100 is equal to, we will get the 75 percentage. Now sp3d hybridization. Now one s orbital and three p orbitals and one d orbital. Here one s orbital and three p orbitals and one d orbital intermixing to forms the 5 sp3 hybrid orbitals. This process is known as a sp3d hybridization. Example, PCl5. In this PCl5, the central atom is phosphorus. Its atomic number is 15 and its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p3. In excited state, the 3s orbital is enter into 3d orbitals. In its excited state, the 3s orbital is enter into 3d orbitals. Now, one 3s orbital, three 3p orbitals and one 3d orbital of phosphorus atom intermixing to forms the 5 sp3d hybrid orbitals. These 5 sp3d hybrid orbitals have unpaired of electrons. So, these 5 sp3d hybrid orbitals of unpaired of electrons overlap with the 3pz orbitals of the chlorine atom to forms the 5 sigma bonds. Okay, then the shape of this sp3d hybridization, the shape is trigonal bipyramidal and the bond angle is 90 degrees or 120 degrees. In this shape, the sp3d and this p bonds, that means p and cl bonds are coplanar. In this 3 sigma sp3d p or 3 pcl bonds, these are in coplanar. The remaining two pcl bonds are axial in position, so that shape is trigonal bipyramidal. sp3d2 hybridization. In this 1s orbital, 3p orbitals and 2 d orbitals, 1s orbital, 3p orbitals and 2 d orbitals intermixing to form the 6 sp3d hybrid orbitals. This process is known as sp3d hybridization. Example, SF6. In this SF6, the sulfur is the central atom. Its atomic number is 16. Its electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p4. It is in ground state. In its excited state, the s orbital and px orbital of the electrons are entered into 3d orbitals. In its excited state, and s orbital and one 3px orbital of the electrons are enter into 3d orbitals. Then now one 3s orbital and three 3p orbitals and three 3d orbitals intermixing to forms the 6 sp3d hybrid orbitals. These 6 sp3d hybrid orbitals has unpaired electrons. So these are overlap with the 2pz orbital of the fluorine atoms to forms the 6 sigma bonds. Now, here the shape is octahedral and bond angle is 90 degrees. Now, let us discuss bond parameters. These are bond length, bond order, bond angle, and bond enthalpy. Bond length means the distance between the two nuclei of the atoms in a molecule. This is the distance between the two nuclei of these two atoms, R1 and R2. Bond length is total bond length is equal to R1 and R2. What is the R here? What is the R1 here? What is the R2 here? The R1 is the atomic radius of this atom. What is the atomic radius? The distance between the nucleus to outermost electron of the shell. That is called the atomic radius. Bond length means the distance between these two nucleus of the atoms in a molecule. The units of this bond length, it is expressed in angstroms, centimeters, meters and picometers. The bond length is inversely proportional to the bond order. Here the bond length of the some molecules. Here ethane, the bond length is 1.54. In ethylene the bond length is 1.34 angstroms. In acetylene the bond length is 1.20 angstroms. If you observe here, the bond order increases, then the bond length is decreasing. So what is the bond order first of all? Okay, the bond order is nothing but a number of bonds between two atoms in a molecule. Bond order is nothing but a the number of bonds between two atoms in a molecule. For example, here H2 molecule. In H2 molecule, two hydrogen atoms has single bond. Okay, so this bond order is 1. Here the in oxygen molecules, between these two oxygens two bonds are present, that is double bond. So the bond order is 2. In N3, in N2 molecule, between two nitrogen three bonds are present, that means it has triple bond. So the bond order of N2 is 3. The bond order is nothing but number of bonds between two atoms in a molecule. So the bond length is inversely proportional to the bond order. Here this acetylene, the bond order is 3. In ethylene, the bond order is 2. Here ethane, the bond order is 1. So whenever the bond order is increasing, the bond lengths are decreasing, so that the bond length is inversely proportional to the bond order. Bond angle. The bond angle is nothing but the angle between the orbitals containing bonding electron pairs around the central atom in a molecule, or in a molecule the angle between 10 atoms. Bond angle is nothing but in a molecule the angle between two adjacent covalent bonds which are linked to a central atom is called bond angle. Okay, it is determined in degrees. It is determined experimentally by spectroscopic method. In water molecule, the bond angle between these two adjacent covalent bonds is 104.45 degrees. Bond enthalpy. Enthalpy is nothing but energy also. The amount of energy is required to break 1 mole of bonds of a particular type between two atoms in gaseous state. Bond enthalpy is nothing but the amount of energy required to break 1 mole of bonds between two atoms in a molecule. The units of this bond enthalpies are kilojoules per moles or kilocalories per moles. In H2 molecule, two hydrogen atoms are bonded with the one single bond. So, to break this single bond, 435.8 kilojoules per mole energy is required. But in O2 molecule, the two oxygen atoms are bonded with the one double bond. So to break this double bond, 498 kilojoules per mole energy is required. So what you observe here? The bond enthalpy is directly proportional to bond order. That means from hydrogen to oxygen, here the bond order is increasing. Whenever the bond order is increasing, here the bond enthalpy also increasing. So the amount of energy required to break 1 mole of bond in a particular between particular atoms in a molecule, that is called bond enthalpy. Now, before going to discuss the dipole moment, we will discuss polar covalent bond and non-polar covalent bonds. So, based on nature of the atoms, the covalent bond is two types. Yes, those are non-polar covalent bond. It is also called pure covalent bond. And second one is the polar covalent bond. What is a non-polar covalent bond? It is also called pure covalent bond. The non-polar covalent bond means it is formed between two similar atoms. Two similar atoms, nothing but homo atoms, the same type of atoms. Okay, the non-polar covalent bond is formed between two similar atoms having same electronegativities. In this type of molecule, the bond pair is lies almost in the center. Whenever the bond pair is lies almost in the center, the electron pair is shared equally between two atoms in a molecule. Example, H2 molecule and in Cl2 molecule and in O2 molecules. These are non-polar covalent compounds. For example, in H2 molecule, in this H2 molecule, the each hydrogen required one more electron to get stability. So that here each hydrogen contribute the one electron for sharing. So here this electron pair in this molecule, this electron pair is lie in center of these two atoms. Whenever these in center, then these two atoms share the electron pair equally. Polar covalent bond. Polar covalent bond, it is formed between two dissimilar atoms. That means hetero atoms. These two dissimilar atoms having different electronegativities. Thus, electron pair, that means the bond pair is displaced towards the more electronegative atom side, so that creating partial positive charge on the less electronegative atom and partial negative charge on more electronegative atom. Then the electron pair is unequally shared between these two dissimilar atoms. Example, HCl molecule and HF, H2O, etc. Those are polar covalent compounds. For example, in HCl molecule, this hydrogen has one electron in its outermost shell and chlorine has 7 electrons in its valence shell. So that here chlorine required one electron and hydrogen also required one electron to get stability. Okay, so that here the hydrogen contributes the one electron and chlorine also contributes the one electron for sharing. So now this electron pair, this shared electron pair is moves towards the chlorine side because of the chlorine is the highest electronegative element. That is the reason the chlorine attract this electron pair towards itself, so that it gets the partial negative charge and hydrogen gets the partial positive charge. So that now HCl is the polar covalent compound. Now let us discuss dipole moment. Okay, a polar covalent molecule behaves like dipole. The degree of polarity of bond or molecule is expressed in dipole moment. Okay, what is a dipole moment? It is a product of the magnitude of the charge and either of the atom and the distance between the centers of positive and the negative charges. That is called dipole moment. What is a dipole moment? The product of magnitude of the charge and either of the atoms and the distance between the centers of positive and negative charge. That is called dipole moment. It is denoted with the mu. Mathematically, mu is equal to q into r. Here q is nothing but charge and either of the atoms, and r is nothing but distance between these two positive and negative charges. It is expressed in dBA. 1 dBA is equal to 1 into 10 to the power of minus 18 ESU centimeters. ESU is nothing but electrostatic units. It is in CGS units. Or 1 dBA is equal to 3.33564 into 10 to the power of minus 13 coulomb meters. Here, the dipole moments units in CGS, ESU centimeters, in SI coulomb meters. The dipole moment is a vector quantity. It is indicated by an crossed arrow having this symbol pointing towards the negative end. Always you keep the symbol towards the negative end in this dipole moment. The dipole moment is caused by both bond pair and as well as lone pair. But the dipole moment caused by the lone pair is more than bond pair. Here, the dipole moment of HCl. The dipole moment of HCl may represented as like this. Here, this bond, the crossed arrow having symbol, this is the symbol pointing towards the negative end. And dipole moment has magnitude and a direction. In case of polar diatomic molecules, there is only one polar bond. Okay. In case of polar diatomic molecules, in case of polar diatomic molecules, there is only one polar bond. So dipole moment of molecule is equals to dipole moment of the polar bond. Applications of dipole moment. The dipole moment is predict the polarity of the molecule. How we identify the given molecule is polar or non-polar? The polarity of the molecule is identified by the if a molecule with dipole moment is greater than 0, that means if not equal to 0, a molecule with dipole moment is greater than 0 or not equal to 0, then the molecule is said to be polar. If a molecule with dipole moment is equal to 0, if the molecule with dipole moment is equal to 0, then that molecule is said to be non-polar. And also the dipole moment is predict the shape of the molecule. And also this dipole moment is used to calculate the percentage of ionic character of covalent bond. Already we discussed the covalent compounds are not 100% and the ionic compounds are also not 100% are possible. The covalent compounds have some of the ionic characters and ionic compounds have some of the covalent characters. So that it is used to calculate the percentage of ionic character of covalent bond. Now the percentage of ionic character of covalent bond is equal to mu experimental value by mu calculated value into 100. So that you remembered here, if the mu is equal to 0, that means the dipole moment of the molecule is equal to 0, then that molecule is said to be non-polar. If the molecule mu value is not equal to 0, that means the greater than 0, then the molecule is said to be polar. For example, in case of polyatomic molecules, there are more than one polar bonds. So that in such cases, the dipole moment of a molecule is the vector sum of the dipole moment of various bonds. For example, in water molecule, this water molecule has more than one polar bond, but means it has two polar bonds. So that in such type of cases, in this type of cases, the dipole moment of the molecule is equal to this vector sum of these two dipole bonds. Okay, in this type of molecule, the dipole moment of this molecule is equal to vector sum of the dipole moment of these two bonds. Okay, then in this water molecule, the water molecule has bent structure, we know that, and the two OH bonds are oriented at an angle 104 degrees, we know that. What is the bond angle in water? Its bond angle is 104.5 degrees. So now net dipole moment of bond moments of two OH bond is greater than 0. That is because of in this the orbital dipole moment due to lone pair. Here the water has lone pair, we know that. That is the orbital dipole moment. The orbital dipole moment due to lone pair is in the same direction, is in same direction as the resultant dipole moment of two OH bonds. If you observe here, these all are in same direction. That means these are not exactly in opposite directions. That is the reason the net dipole moment is greater than 0, because of the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of two OH bonds. So that net dipole moment of water molecule is greater than 0. Whenever the dipole moment is not equal to 0 or greater than 0, then that molecule is said to be polar. So here the water molecule is polar molecule. Now let us discuss BeF2 and CO2 molecules. In this BeF2, the BeF bonds are polar, but BeF2 molecule is non-polar. What is the reason? Then how these BeF bonds are polar? Because of in this BeF bond, the fluorine has the highest electronegativity value. So that this fluorine is attract the electron pair towards itself. That is the reason it gets the partial negative charge and beryllium gets the partial positive charge. So that BeF bonds are polar. But BeF2 molecule is non-polar. Because of in this BeF2 molecule, net dipole moment is 0. Because the net dipole moment of bond moments of these two BeF bonds is 0. Because of these two BeF bonds are opposite in directions, so that these are cancelled to each other. That is the reason the net dipole moment of BF2 is 0. Whenever the mu is equal to 0, whenever the mu is equal to 0, the molecule is said to be non-polar. So here the BF2 molecule is non-polar, even though the BEF bonds are polar. Because of the BEF, two BEF bonds are, the bond moments of two BEF bonds are in opposite directions. Whenever these are opposite directions, these are cancelled to each other. Then we get mu is equal to 0. Whenever the mu is equal to 0, the molecule is said to be non-polar. So that BF2 molecule is non-polar, even though BA bonds are polar. Next goes to water molecule. Sorry, CO2 molecule. In this, it is also linear structure. It is also linear structure, so that the net to dipole moment of bond moments of two CO bonds is 0. Because of here also, these two CO bonds are exactly in opposite directions. Whenever these are exactly in opposite direction, these are cancelled to each other. So that here the mu is equal to also 0. Whenever the mu is equal to 0, the molecular said to be non-polar. So here the CO2 molecule is also non-polar because of the mu is equal to 0. Next goes to in BF3 molecule. In BF3 molecule, the BF bonds are oriented at an angle 120 degrees. Okay, in BF3 molecule, the BF bonds are oriented at an angle of 120 degrees to one another. But here the dipole moment of BF3 molecule is 0. Okay, in this BF3 molecule, these BF bonds are oriented at an angle of 120 degrees to one another, even though the dipole moment of the BF3 molecule is 0. Because of here, these two bond moments, because of these two bond moments are equal and opposite to the third bond moment. Here, these two bond moments are these two bond moments are opposite to third bond moment. That is the reason here when these are each other, then mu is equal to 0. Whenever the mu is equal to 0, the molecule is said to be non-polar. So that the BF3 molecule is non-polar. Next goes to, we will observe the NH3 and NF3 structures. If we will observe these NH3 and NF3 structures, in this, these two are pyramidal in their shapes. Yes, these are pyramidal shapes and they have one electron pair on nitrogen atoms. Okay, but also here the NH3 has dipole moment than the NF3. Here these two structures are pyramidal in shapes and also they have one electron pair on nitrogen atoms. Okay, but also here the NH3 has higher dipole moment than the NF3. What is the reason? Because of in this NH3 molecule, because of in this NH3 molecule, the orbital dipole, this is the orbital dipole. The orbital dipole due to lone pair, this orbital dipole due to lone pair is in same direction as the resultant dipole moment of these three NH bonds. Whereas in NF3 molecule, the orbital dipole, this orbital dipole due to lone pair is in the opposite direction to the resultant dipole moment of three NF bonds. Because of
This orbital, because of lone pair, decreases the effect of the resultant NF bond moments. That is the reason the NH3 has higher dipole moment values than the NF3. Then assignment related to this topic. What do you understand by hybridization? And explain different types of hybridization involving S and P orbitals. And one more, NH3 has higher dipole moment compared to NF3, even though both NH3 and NF3 are pyramidal. Why? Next goes to, let us discuss molecular orbital theory. It was proposed by Hun and Mulliken. Okay, it was proposed by Hun and Mulliken. In this molecular orbital theory, the atomic orbitals have same energy or nearly same energy and proper symmetry combined to form molecular orbitals. In these molecular orbitals also, the atomic orbitals have same energy or nearly same energy and proper symmetry combined to form molecular. That means the molecular orbitals are formed by linear combination of atomic orbitals of same or nearly same energies. That means this theory is explained by the LCAO method. What is the LCAO? Linear combination of atomic orbitals. Okay, whenever two atomic orbitals combine, whenever two atomic orbitals combine to form two molecular orbitals. Okay, whenever two atomic orbitals combine to form two molecular orbitals, those are, one is bonding molecular orbital and another one is anti-bonding molecular orbital. If you observe here, these atomic orbitals, SS atomic orbitals undergoes to combine through the LCAO method to forms the bonding molecular orbitals and anti-bonding molecular orbitals. What are the bonding molecular orbitals and anti-bonding molecular orbitals? Okay, here the bonding molecular orbitals means the molecular orbitals are formed by the molecular orbitals which are formed by additive effect or constructive interference of the atomic orbitals is called bonding molecular orbitals. Okay, the molecular orbitals which are formed by additive effect or constructive interference of the atomic orbitals is called bonding molecular orbitals. The anti-bonding molecular orbitals means the orbitals which are formed by subtractive effect or distractive interference. Okay, the anti-bonding molecular orbitals means the molecular orbitals are formed by subtractive effect or distractive interference of atomic orbitals is called anti-bonding molecular orbitals. The molecular orbitals are formed by the additive effect or constructive interference of the atomic orbitals are called bonding molecular orbitals. The molecular orbitals are formed by the subtractive effect or distractive interference of the atomic orbitals are called anti-bonding molecular orbitals. Here, the molecular orbitals which are bonding molecular orbitals has lesser energy and greater stability. These are represented with the sigma and pi. Then anti-bonding molecular orbitals has higher energy and lesser stability. These are represented with the sigma star and pi star. Here, these are atomic orbitals combined to form the molecular orbitals. In these are anti-bonding molecular orbitals. The anti-bonding molecular orbitals are formed by the subtractive effect or distractive interferences. is called anti-bonding molecular orbitals. Then these are having the higher energy and lesser stability. These are denoted with the sigma star and as well as pi stars. Then here bonding molecular orbitals. These bonding molecular orbitals are formed by the additive effect or constructive interference of the atomic orbitals. Bonding molecular orbitals. The bonding molecular orbitals have lesser energy and greater stability. These are represented with the sigma and pi. Then of the number of molecular orbitals. These are molecular orbitals. The number of molecular orbitals are formed are equal to the combining atomic orbitals. Okay, the number of molecular orbitals formed in this process are equal to the number of combining atomic orbitals. And one more thing, the electrons of atoms present in atomic orbitals. Okay, the electrons of atoms present in atomic orbitals, whereas electrons of molecules present in molecular orbitals. Okay, these are the atomic orbitals and these are the molecular orbitals. These are formed by the LCO method by the atomic orbitals. Then order of molecular orbitals. In this, the bonding anti-bonding molecular orbitals are higher energy and lesser stability than the non-bonding molecular orbitals. Non-bonding molecular orbitals are nothing but atomic orbitals. And these non-bonding molecular orbitals have higher energy and lesser stability than the bonding molecular orbital. The bonding molecular orbitals has lesser energy and high stability. The molecular orbitals, like atomic orbitals, are filled in accordance with above Pauli's and Hund's rules. It is also explain the magnetic nature of the molecule. It is also explain the magnetic nature of the molecule. And also it is used to calculate the bond order. Then how to calculate the bond order? The number of electrons in bonding molecular orbital minus the number of electrons in anti-bonding molecular orbitals by 2. How to calculate the bond order? The bond order is equal to the number of electrons in bonding molecular orbital minus the number of electrons in anti-bonding molecular orbitals by 2. So it is the shortcut NB. NB is nothing but a number of electrons in bonding molecular orbitals minus Na. Na is nothing but number of electrons in anti-bonding molecular orbitals by 2. Then how to identify the magnetic nature? How to identify the magnetic nature? If the atom or molecules have unpaired of electrons, then that molecule is said to be paramagnetic molecule and also that exhibit the paramagnetic nature. If the molecule or atoms have paired of electrons, if the molecules or atoms are paired of electrons, then that molecule or the atom is exhibit the diamagnetic nature. Then electronic configuration of molecules contain 14 electrons or more than 14 electrons. For example, O2 and F2 molecule. The electronic configuration of molecules contain 14 electrons or more than 14 electrons. Example, O2 molecule. The O2 molecule is from the combination of two oxygen atoms. Yes, actually the oxygen atomic number is 8. So here two atoms are combined to form the O2 molecule. So in this O2 molecule, how many electrons are present? 16 electrons. And same as well in fluorine molecule. The fluorine molecule is formed by the combination of two fluorine atoms. The atomic number of fluorine is 9. So two atoms are combined to form the F2 molecule. So now F2 molecule has how many electrons? Now 9 plus 9, 18 electrons.
So it is applicable. This electronic configuration applicable for the molecules containing the 14 electrons or more than 14 electrons. Then energy levels. That means how two electrons entered. Here the first electron is entered into sigma 1s orbital. Then further it is entered into sigma star 1s. The next the electrons are entered into sigma 2s. The next the electrons are entered into sigma star 2s. The next electrons are entered into sigma 2pz. The next pi 2px and pi 2py. These are degenerate orbitals. The pi 2px and the pi 2py are degenerate orbitals. And next electrons are entered into pi star 2px and pi star 2py. These are also degenerate orbitals. The next electron is entered into sigma star 2pz. The electronic configuration of molecules contain less than 14 electrons. Okay, the electronic configuration of the molecules contain less than 14 electrons. For example, lithium molecule and beryllium molecule, boron molecule, carbon and N2 molecule. How to write these electronic configuration? First of all, these are electrons enter into sigma 1s, next enters into sigma star 1s, next enter into sigma 2s, next, electrons enter into sigma star 2s. Here, the sigma 1s and the sigma 2s are bonding molecular orbitals. Here, the sigma star 1s and sigma star 2s are anti-bonding molecular orbitals. Just now we discussed. Sigma star pi stars are anti-bonding molecular orbitals and sigma pi molecular orbitals are bonding molecular orbitals. The next electron entered into pi 2px and pi 2py. These are also degenerate orbitals. The next electron entered into sigma 2pz. The next pi star 2px and pi star 2py. And next electron is entered into sigma 2pz. Here, electron configuration of the molecules contains contains the 14 electrons or more than 14 electrons, and the electronic configuration of molecules contains the less than 14 electrons is same up to here. But electronic configuration of the molecules contain 14 electrons and more than 14 electrons is different here to here. Up to here, in these two electronic configurations are same up to here, but difference in this here only. In these 14 electrons of molecules, the electron is enter into after 2s orbital enter into sigma 2pz. But in this, the molecules contain less than 14 electrons. The electrons after 2s orbital is enter into pi 2px and pi 2py. And next goes to electron is enter into pi 2px here, pi 2py and pi star 2px and pi star 2py, then sigma star 2pz. But here the electron after this enter into sigma 2pz and pi star 2px, pi star 2py and sigma 2pz. Then now let us observe the mode of H2. That means MOED, that means molecular orbital energy level diagram. MOED means molecular orbital energy level diagram of H2 molecule. Here, this H2 molecule is formed with the combination of two hydrogen atoms. The hydrogen atomic number is 1. Its electronic configuration is 1s1. Here, this H2 molecule is combining by the two hydrogen atoms. So, here the H2 molecule has now how many electrons? 2 electrons. So its electronic configuration is sigma 1s2. Okay. Then here these are atomic orbitals of hydrogen atoms and these are molecular orbitals of H2. Okay. Now here the one hydrogen atom electronic configuration is 1s1 and another hydrogen atom electronic configuration is 1s1. Then in this molecule is formed by the combination of these two hydrogen atoms. Then these two electrons are entered into first sigma 1s orbital. This is the bonding orbital, and this is the anti-bonding orbital. Then now how to calculate the bond order? Then bond order is equal to the number of electrons present in the bonding orbitals minus the number of electrons present in the anti-bonding molecule, anti-bonding orbital by 2. Here in this, how many electrons are present in this bonding orbital? 2 electrons. So 2 minus how many electrons present in the anti-bonding molecular orbital? There is no electrons. So 0 by 2, that is equal to 1. Bond order is 1. Then H2 bond order is 1. It exhibits the diamagnetic nature. It exhibits the diamagnetic nature because of it has absence of unpaired electrons. That means in these molecular orbitals, the orbitals are total filled with the electron. That means it does not have any unpaired electrons. That is the reason it exhibits the diamagnetic in nature. Next goes to B2 molecule. Mode of B2. Molecular orbital energy level diagram of B2. Here in this, the B2 molecule is formed by the combination of two boron atoms. The boron atomic number is 5. Its electronic configuration is 1s2, 2s2 and 2p1. That means each boron has 5 electrons. Then in this B2 molecule, the B2 molecule has 10 electrons. Okay. Then electronic configuration of this B2 molecule. The electrons are entered into sigma 1s2. Then electrons are entered into sigma star 1s2 and sigma 2s2, then sigma star 2s2, and then pi 2px1 and pi 2py1. These are degenerate orbitals. Okay. Then how to fill the electrons in these? Here, these are the boron atoms electronic configurations. Okay. These are the boron atom electronic configurations. These are boron atom electronic configurations. And these are the B2 molecule orbitals. Then now here boron electron configuration is 1s2, 2s2 and 2p1. Then now the B2 electronic configuration is sigma 1s2 and sigma star 1s2 and sigma 2s2 and sigma star 2s2, and next to fill
Madam,
the electrons. Sir.
kindly close the
Okay, sir. Okay, let us then you will write the now MOED of N2 molecules and MOED of O2 molecules. It is easy. If you understand this concept, it is very easy. Thank you, one and all.